Hi folks, it's David Kearns here with a Sharpie video for you today. Today's video was prompted by a question that I received recently online, which was asking why thermal power stations throw away so much of the energy that they have. If you look at a picture of any large thermal power station especially, you'll see these large plumes of steam coming out of their cooling towers. And it's a reasonable question. Why is it that they burn all of this fuel, produce all of these emissions, and then just throw so much of that energy away rather than turning it into electricity? Why don't we try and turn more of that heat that we get out of burning our fuel into electricity? So I wanted to go through fairly quickly today with my Sharpie exactly why that is. So enjoy. So today's question is, why do power stations throw away heat? So we'll just get back very quickly to the fundamentals of what exactly a power station does. So I'll represent a power station with this lovely black box, and here's our power station, PS. What does a power station ultimately do? It takes in a fuel of some kind. So it might be, in this instance, coal or natural gas, or maybe a biofuel. It doesn't really matter. Anything that it can combust and create something hot. And so we've got here coming in is a fuel. And what it produces as its product, ultimately coming out the other side, is electricity. But it also produces something else, which is what we call waste heat. And the question is, why is it producing that waste heat? Why would we go and burn all of this lovely expensive fuel of ours when we want to make electricity, but we're producing some waste heat? Well, let's take a step back for a moment and look at what a very famous scientist in the 19th century in France called Sadi Carnot. Sadi Carnot developed what is known as a perfect theoretical heat engine. So what does that mean? Essentially, it's a box, and I won't go into the details of what's inside that box, but effectively what he said is, if we take a source of heat, so this is energy flowing from something that's hot, and we convert that perfectly as anything can be done in our known universe, we will produce what is known as work. Now, work is essentially any energy that we can use and convert perfectly into other forms of energy, so electricity is a form of work. And what he found that was, even with a perfect engine, so I'll say here this is perfect. Now this is in theory, this can't be made in practice. He found that you would still produce waste heat. And so effectively what that means is that if we took all of this heat energy, and the conventional symbol for heat in engineering is the symbol Q. So Q is the amount of heat in kilojoules or megajoules or whatever units you care to mention. You will get a certain amount of work, which we call W, and you'll get a certain amount of waste heat, which we can't use, which we have to throw away. And that's even with a perfect world. And what he discovered is that this ratio between the amount of work that we get for the amount of heat that we produce, we call thermal efficiency. So thermal efficiency is what fraction of the heat energy can we convert into work, electricity, or whatever we care about. And what he discovered is that that's actually equal to, in a perfect engine, the best thermal efficiency that you could ever hope to achieve is 1 minus the ratio of Tc and Th. So what are they? These are temperatures, and these are temperatures. C is for cold and H is for hot. So H for hot is the temperature of our source of heat, because when we burn a fuel, we make something hot. That's the source of our heat. So it has a temperature, Th. When we reject our heat to the environment, this waste heat here, it actually is rejected to the environment at some lower temperature. So typically, if you want to cool something, you need to reject that heat to a cooler place. So that could be to the air, it could be to cooling water or something like that. And what this tells you is this is like the speed limit, if you like, for generating work from heat. So that's for any kind of thermal power station. That is the best you're going to get. So let me give you a quick example. Let's say that your high temperature is 1000 Kelvin. So that's about, what's that, 727 degrees Celsius. And let's say your T low is ambient temperature roughly. So we'll say it's a warm environment, 30 degrees. 30 degrees is 303 Kelvin. 30 degrees C. A perfect engine where I'm burning a fuel at 1000 Kelvin and I'm rejecting heat, sorry, that should be TC, not TL, at 303 Kelvin, the best efficiency for a perfect world is going to be 1 minus 303 divided by 1000, which will in fact, we make these nice round numbers so I can do this in my head. We'll call that 300 degrees. That's just 1 minus 0.3 equals 0.7 or 70%. So immediately we can say that a perfect engine that is doing everything right and is not wasting any energy along the way can only convert between those two temperatures 70% of the energy that was in the heat into work. And we have to throw the rest away. We can't hold on to it or the whole system will heat up and it will just stop working. And so what does this mean for power stations? What it means is essentially is that fuel energy, or heat if you like, is not equivalent to the amount of work or electricity. So when you hear people talking about amounts of energy in a fuel, like they might be talking about gigajoules of gas, for example, you cannot directly compare those numbers to electricity numbers, which might be in, say, kilowatt hours or megawatt hours or something like that. Even if you convert the units, these things are not equivalent. Essentially, because we can't convert all of the heat we have into work, that means that fuel energy is worth a lot less, a gigajoule of fuel energy is worth a lot less than a gigajoule of electricity energy. And what that does is that has an effective limit on the way that our power stations work, that we can't design. Even in a perfect world, as you could see there, we could get 70% efficiency. In the real world, you might only be getting to 40. So that's just to give you an idea of why power stations throw away heat, because even if they operate perfectly, they are unable to convert all of the heat from burning a fuel into work.